Especially as early career people, like, yeah, we really need this facility, but at the same time, like, we need to be like, do I want to? Could I be finishing a paper? Yes.
Good way to describe it.
Let it be. Where it's like, does no J like this? Like, I'm just the right one.
Yeah, no.
Oh, yeah.
See them. I don't know if it's
It's an awkward time.
the guy who's paying for me. Actual Congress.
I said it to spin, and then like comments.
So one must protect your time. I know we can't. But we're balancing one's time.
Yeah, because like the white papers coming up, it's like these are for receiving HST. Like it's important.
I would love to do it.
It's a lot of work to put together a compelling white paper, and then think just like we're not going to get citations out of it, and we won't even necessarily get public time out of it.
That's a good idea.
No, it's very
Sorry, that was
harder than mine. Back then, the publication record requirement wasn't so high.
well, but yeah, color changing.
Like these.
It's way better to do a white guy. Oh man, so much better.
That sounds like a very emphatic yes.
Yeah.
I think it's basically like
About clowns this morning.
it's like a very broad like
About like
Like this.
almost like an academic.
Yeah, exactly. That's a good way of putting it.
Okay.
It's fun. It can be time consuming, but it didn't take any time. You just like continue this next week.
All right, everybody, welcome back. We are going to start our next session. So today we have a couple talks and then some flash talks to end it with. And so without further ado, Piyush, would you take it off?
Awesome, thank you. Can you hear me all right in the back as well? Can you hear me? Yeah, awesome, thank you. Good afternoon, everybody. I'd first like to thank the organizers for giving me an opportunity to talk about what's happening at low metallicities in the ISM on very, very small scales. I'm currently based in Leiden, but I'm soon moving to STScI. So it's going to be a big change in terms of food. Wait for that. All right. So to sort of set the scene, I thought I'll sort of show why do we really care about low metallicity environments. I mean, we all care about low metallicity environments here quite a lot. But just to sort of see from a cosmological point of view, this is a snapshot from the Colibri cosmological simulations, which sort of shows the evolution of the metallicity in a very large megaparsec, few megaparsec scale size box. And we see that everything that is sort of below solar is what we consider the metal poor universe, right? And there are a lot of environments throughout cosmic history which are very, very metal poor and remain metal poor to the present day. Now, what is one person's metal poor may not be another person's metal poor. So I've sort of created like a scale in metallicity over here, where we are roughly here in the solar neighborhood, but then we go down this scale and there's a huge variety, diversity of astrophysical regions, sources, objects that we really care about when we talk about the metal poor universe. So in some ways, maybe we should call this the metal normal universe, because most of the universe does seem to have low metallicities than the sun or the solar neighborhood. And particularly at high redshifts, as you've already heard quite a lot, we are finding some really, really exciting systems, objects, which we are trying to sort of decipher. From an ISM point of view, I tried to sort of summarize what these observations of the first galaxies with Webb are telling us. And we have already sort of covered some of these points in previous talks as well, where we are looking at ISMs that are very compact, very dense. I've sort of provided some numbers with reference to what we see in the Milky Way to provide some reference scale. If you just put a lot of mass in a very small amount of volume, you are going to be looking at environments which have very, very high amounts of radiation. But these environments seem to have normal-ish star formation rates, perhaps massive black holes, but they have little dust or low metallicities in them. So in this concoction of conditions is not something that we really see in the local universe. If you look at up to 20-like systems, they satisfy all of these things, but they're not metal poor or dust poor. So in that way, these are really like an uncharted territory of ISM conditions, which means we need to sort of go back to our drawing board and understand how stars form in these environments and how feedback occurs. There have been a number of solutions that have been proposed for early galaxy problems, including why do we see so many very, very bright galaxies, blue monsters, we see lots of atypical line ratios, and we've already talked about that quite a lot. We see weird chemical abundances, maybe early supermassive black hole seeding and growth. And here is a range of solutions that I've seen in the literature. I've sort of stolen this slide from Rachel Somerville. But one key thing to see here is that many of these solutions depend on what goes on in the ISM at or below cloud scales. And that is a perspective that I'll try to bring in this talk today and try and convince you that looking at the very, very small scales in the ISM, so going scales from few parsecs down to where stars are actually forming, is quite important. And there are quite a lot of surprises that are there at these when you go to low metallicities and you try and resolve those scales. So what does the cloud scale ISM look like, right? I mean, if you start from molecular cloud scales, so again, parsec scales, we know that these clouds will collapse. And the main condition for forming stars is that you need to have enough mass in the cloud so that gravity can overcome other forces and form stars. And this mass is characterized with the Jeans mass, which depends on the temperature and the density. So basically, if you can characterize the temperature and density of a cloud, you can sort of gather some expectations for what sort of stars would we form in that environment. But we often don't appreciate that there is still a huge dynamic range of ISM physics that happens from the time clouds start collapsing to the time we actually start forming stars. And that's the sort of physics I'll talk to you about today, and the challenges therein particularly. So we have all had lunch. If you're feeling sleepy, if you're not feeling sleepy, maybe the next few slides will make you feel sleepy. I'm not going to present any solutions. I'm just going to bring you a lot of problems at low metallicities when we go down to these sorts of scales. All right. So the first one is, how does cooling and chemistry in the ISM occur at low metallicity? So for this slide, imagine all of us are ISM theorists. We are trying to understand, as the cloud is collapsing, how is the temperature of that gas in the cloud changes as the density increases. All right, so this is density on the x-axis, temperature on the y-axis. Notice that this is log in density, right? So you're covering 18 orders of magnitude in density over here. Molecular clouds are somewhere around here. So they still have to cover 18, 20 orders of magnitude in density to form a star eventually, right? Now, let's do this at different metallicities. So solar, 10% solar, 1% solar, all the way down to primordial metallicities. And it turns out that when you start to just solve for chemistry of the gas together with heating and cooling and all these sorts of reactions, you see that the temperature the gas follows is quite different as you go to lower metallicities. In particular, at lower metallicities, we also have low dust, and low metals and dust make cooling in the ISM very, very inefficient. And this cooling is then more sensitive to whatever amount of metals you do have present, and their abundances cannot reach equilibrium. So non-equilibrium effects in the ISM chemistry become really, really important as we go to lower metallicities. You can also imagine that because you go to lower metallicities, the temperatures are higher, which means the Jeans masses are higher, and that's a very zeroth order expectation for why we should expect more massive stars as we go to lower metallicities. So what do we really need to do? We need to include on-the-fly chemical modeling for low metallicity ISMs. So if you're going below metallicities of 10% solar, keep in mind what the chemistry of the gas is doing, because that impacts everything about star formation and feedback and so on, and the IMF as well. So that's the first challenge. Another challenge is how does shielding occur in dust poor or metal poor gas? So I realized that I'm talking a lot about neutral and dense gas, by the way, which we haven't maybe heard about as much in this conference so far. So I'm giving you a perspective on what happens in very, very dense gas. Now, in general, we know H2 is important because that's what ultimately creates stars. And we also know that H2 can self-shield itself against some of these Lyman-Warner photons, so photons in the far UV band. If H2 is not able to shield itself, then the entire star formation physics changes quite a lot. Now, what happens in dust-poor regimes is that as this H2 gets dissociated because of far UV photons, you start to create a very thick layer of H1 around this gas. And if you do not have enough dust, this H1 starts to provide additional shielding. And that matters a lot if you are in very, very low or dust-poor environments. How does it matter? Here is sort of a controlled 3D MHD simulation where we have chemistry on the fly included. And we look at two different simulations, one where this shielding is not included, and that is the norm. We don't think about shielding of H1 by H2 as much in dense gas. And one where this is included, and you see that eventually the masses of the stars in this very, very controlled numerical experiment start to diverge quite a lot, to the point where ultimately the ultimate fate of these stars also changes. In one case, you get a pair instability like supernova. In another case, because of extra shielding, you can sort of create more massive stars, which maybe end up as black holes. So we need to incorporate these cross-shielding effects, and in particular, more generally, we need to incorporate line shielding effects in dense gas, in dense metal-poor, dust-poor gas. Okay, the next slide is my favorite, because most people don't want to talk about this. I don't know if anyone else is going to talk about magnetic fields, but when we go to lower metallicities, magnetic fields are also very important. They are important at all metallicities for star formation. This is now a norm at solar metallicity, but at low metallicities, we don't really understand what happens. And we've been trying to explore this more and more. So what you will see in this particular movie is 4 simulations. One which is HD, means hydrodynamics. Here, magnetohydrodynamics. This is radiation hydrodynamics, which means we include effects of ionization and dissociation of the gas from the stars that are forming. And this is radiation magnetohydrodynamics, where you include all of these sorts of effects together. And we are looking at GMC scales, resolving down to AU scales to understand how individual stars, whether they are low mass or massive, how they form, how they evolve, and what masses they gain. So this is going to be the density, this is the temperature, and this plot will show you how the most massive star is evolving. If I just play the movie, you see right from the very onset that the way the most massive star evolves in the presence of magnetic fields is wildly different. So in particular, magnetic fields in a way sort of act to limit the most massive the stars can become at low metallicities. This is very similar to what happens at solar metallicity, but just that in the absence of dust and metals, the room that magnetic fields have to play is quite large and quite important. So in some ways, I like to say magnetic fields play an even more important role in star formation and feedback at low metallicities than at solar metallicity, which means that including MHD in any sort of a low metallicity ISM calculation or simulation in particular is quite important. They also impact things in other ways. So for example, and this has already been covered in some other talks as well, but also from a star formation perspective, we do see that most massive stars do not evolve in isolation, at least when they are forming. So most of these massive stars do have companions around them. This plot shows the mass of the star forming the simulations as a function of the multiplicity fraction, or what is the probability that the star has a companion. And you see that as you go to masses more than 8, 10 solar masses or so, almost none of the stars are single stars. So at least binaries, triple systems, sometimes even higher order systems that may or may not survive. In the presence of magnetic fields, we also find that we create metal-free binaries at smaller separations. So if you like having BPAS models, metal-free, metal-poor binary models, this is good news, because we do see that if we include all of the physics, there is a tendency for us to create more compact, massive metal-poor binaries. But we don't have the resolution really to sort of resolve the formation of very compact metal-poor binaries, and that's what we sort of need to include in our simulations. So I'm sort of giving you like a one-slide overview of all of these different physical processes that go on in the ISM and how or why they are different at low metallicities or in dust poor. Radiation feedback. So basically how stars produce photons that ionize and dissociate the gas around them. They drive H2 regions and so on, stellar winds, and how that looks quite different if you do not have enough dust. And the main fundamental thing here is that in a metal-rich, dust-rich environment, the dust sort of absorbs that radiation and then transmits it to the gas. But if you remove dust from the equation, or if you remove like a lot of dust from the equation, then that coupling between radiation and thermodynamics of the gas fundamentally changes. So it is much more sensitive to the chemistry of the gas. So in these dust-poor, metal-poor environments, we need to sort of better understand how chemistry in the ISM couples with radiation. And that's what has led to a lot of debates in the literature, where in some cases, for example, we see these bipolar H2 regions, which are also, by the way, very, very turbulent. They're like some stars of like 30 to 40 solar masses in here, which drive these biconical outflows and create H2 regions. This is where the accretion disk of the stars is. But in other cases, we don't see any evolution of H2 regions. So how H2 regions evolve remains a very active topic of debate. Of course, we see that they ionize the universe. You have photon leakage occurring on larger scales, but we don't really understand how does it start, where to sort of inject these photons into the first place from the stars. So we need more sophisticated treatments of radiation in these sorts of environments. And let's say you don't care about the ISM physics as much, you really want to know what are the final masses of these stars when we include all of these ISM calculations into account. Here is sort of another example that sort of we did, looking at how stellar evolution is impacted. And I think one of the main things that we are finding is that massive stars reach the zero-age main sequence pretty early. That's not new. But in metal-poor conditions, they continue to accrete also on the main sequence. So it is not that you have your pre-main sequence phase, then you do stellar evolution modeling for the main sequence phase by keeping the mass of the star fixed. In many cases, it is likely that these stars are still accreting while they're on the main sequence. In fact, if I look at some recent web results in the LMC, so not super metal poor, but half solar metallicity, people are now finding even around low mass stars, which are very old, they're still continuing to accrete. So 40 million year old low mass metal poor stars are still accreting in the LMC. So if you think about the IMF, it sort of breaks down, because by the time your low mass stars haven't finished forming, your massive stars have already gone. So this sort of makes the whole problem of what is the IMF at low metallicities even more complicated. So we need to include self-consistent modeling of stellar evolution physics with star formation physics, because of course, what happens in the stars then feeds back through radiation feedback into the gas, and then that changes how the stars are accreting. But the main message here is that these stars are still accreting on the main sequence. So we need to sort of take that into account in our modeling. And let's say we have done all of this. Stochasticity still remains a big factor. And we've already heard from Evan and other people as well about how this plays a big role. But I'd like to highlight here that stochasticity means different things. Like you can have different types of stochasticity in the ISM, right? One is something that Evan has already talked about, which is you cannot sample the IMF very well. And that's largely because we have fewer stars forming at lower metallicities in a given cluster. But the other is because of turbulence. And that remains quite an important factor governing ISM physics, all sorts of things that we care about in the ISM. Turbulence plays a very big role there, also at lower metallicities. So here is another controlled experiment where what you're seeing in each column is exactly identical initial conditions for a GMC scale simulation, where you then resolve down to AU scales and form stars. We're only changing the random seed, so sort of changing the initial turbulent distribution or the velocity field of the gas. And you see that at lower metallicities, the outcome in terms of the number of stars, the masses of the stars, is completely different. So we need to do a lot of these experiments and simulations to be able to generate something that is a bit more statistical. So the impact of stochasticity increases as we go to lower and lower metallicities. Okay, there are other challenges as well. I sometimes feel that this is maybe too negative of a talk, but it's worth highlighting. So you can imagine, right, that if you think about all of these sorts of different things that are happening in the ISM on small scales, you're going to get different masses for the stars, which means your IMF would look something different at low metallicities. So before we do like full-fledged 3D hydro simulations with all of the physics included, we can sort of start to develop some intuition based on phenomenological models for what the IMF variation should look like as a function of metallicity. And that's what we have been also doing on the side, where we're trying to understand how the characteristic mass or the peak or turnover mass of the IMF changes as you go to lower metallicities by solving for radiation feedback with chemistry in particular in these models. And we see that as we go from solar metallicity over here to lower metallicities here, the characteristic mass sort of evolves quite a lot. At solar metallicity, there is not a lot of variation, which sort of gave rise to the age-old idea of a universal IMF. But if you go down to lower metallicities, it starts to show some really interesting trends. And this is largely driven by what is happening in ISM in terms of chemistry. Here, when you are very metal rich, dust governs a lot of your gas thermodynamics on these scales. At lower metallicities, line cooling because of metals, and then H2 and primordial cooling take over. Now, the interesting thing here is that this is actually a regime where we are now starting to maybe test for IMF variations in our own galaxy. This is some really interesting work going on where people are starting to look at outer Milky Way, so going 15, 20, 25 kiloparsecs from the galactic center, and with Gaia DR3 and some sort of under-the-box magic, they can sort of look at how this characteristic mass for these young star clusters in the outer Milky Way would vary. There are lots of uncertainties there, but we are sort of starting to see some trends that we see in these models as well, where we see some sort of an evolution in the characteristic mass that may or may not be just simply monotonic. Now, all of this is also impacted by non-solar scale abundances at low metallicities, which has already been touched upon a little bit. So for example, we know very well from work by Daniel, but also looking at metal-poor stars with very exquisite spectra where we can measure 3D non-LT abundances as well, that the carbon over oxygen ratio is not solar. Now, it turns out that if you have less carbon in the ISM, it also matters a lot for cooling, not surprising, but it also matters a lot for what sort of a stellar mass distribution would you get out of such an ISM. So if you start from an ISM that is carbon poor, you get different answers for the masses of the stars, particularly at low metallicities. And this is what this plot is showing here. Again, the characteristic mass as a function of metallicity. And you see that there is a factor of 7 almost difference when you go to lower metallicities and you start using non-solar scale abundances. And a factor of 7 in stellar masses is quite large. Doesn't happen all the time. In very, very high pressure environments, it may or may not be super relevant, but we do need to take these COO variations into account. Okay, so what is the full picture then? All of these cloud scale effects, they tend to set the outcome of star formation. They modulate the efficiency of star formations if you care about bursty star formation, how feedback occurs on large scales, and so on. This stuff seems to change all of that, and in some ways very dramatically when we go down to lower metallicities or lower dust to gas ratios and so on. And this is what we are trying to sort of build towards, to create a theoretical or numerical framework that can include as many of these physical processes as possible, still be able to simulate this in a somewhat like computationally feasible amount of time. And that's what we have been trying to do with the Popsicle project, which stands for Pop 2-3 simulations, including all of these. We came up with the acronym first, and then we were like, oh, now we have to include all of this physics because otherwise the acronym doesn't work. So it's sometimes helpful to think about your acronym first in astronomy. So what are we doing? We are sort of looking at environments that are 10% solar and below, with chemistry, non-equilibrium chemistry, with some sophisticated schemes for radiation, which is coupled to chemistry, with some really high genes resolution. You can ask me about that later, to very importantly resolve the impact of magnetic fields, and that is the bottleneck. Magnetic fields sort of require a lot more resolution. So if you simply put them in and you don't see anything, that doesn't mean they're not doing anything. And calibration free, there's no calibrations to be done here anyway. And the idea here that we have is to be able to produce some realistic IMFs at low metallicity by resolving this star formation down to AU scales, so we can sort of understand how stars are forming, how are they gaining mass from their accretion disks, how fragmentation occurs, how do you get binary systems, triple systems, and how do you really develop an IMF from first principles, which then automatically feeds into the second goal, which is to explore black hole seeding in dense but dust poor, metal poor star clusters. And the third point is something that people who are more interested in larger scales trying to use the same numerical framework to look at. So what we can do with these sorts of ingredients in place, we can then start to look at how dense, compact, metal poor star clusters would form. And the main thing here, like I said in the beginning, is chemistry. So chemistry in dense gas, not just chemistry for carbon, but also chemistry for oxygen. So this is a very well-known sort of a PDR model, sort of a plot in the ISM, where you see that at low densities, most of your carbon is C+, then it becomes C1, then it becomes CO. And similar transitions also occur for oxygen-based species like O and OH and H2. And the reason I'm bringing all of these species, you may not have really seen them as much, is because they are very important at low metallicities. When you go below 10% solar, OH and water in particular become quite important too, and they govern a lot of your cooling and chemistry as well. And then we can sort of start to see on star cluster scales, where is the ionized gas sitting, where is your H2, what is actually tracing the dense gas. In some cases, even at solar metallicity, CO is not a very good tracer of H2 in these conditions. So you do get a lot of CO dark gas, and other tracers become more important. And that's what we're trying to sort of produce from these simulations. Now in my last 0 minutes, 2 minutes, I'll talk quickly about, okay, you do all of this, what about the IMF? Like I said, at low metallicities, in some ways, the concept of an IMF could break down if your stars are not all forming at the same time. But compared to population 1, or the IMF in the Milky Way, where we think physics like radiation and magnetic fields set different parts of the IMF in these ways, we're finding that, for example, at very low metallicities or zero metallicities, the way these physical processes influence the IMF can be completely different. So different parts of the IMF are not being set by the same physics anymore, which also is not surprising that you get very different IMFs. In some cases, you have these little blips over here. So these are your very, very massive stars. One of them will completely dominate whatever you find on larger scales as well. But there's a lot of stochasticity here. The sampling is a problem. And there is likely no unique POP2 or POP3 IMF. So it sort of even adds to the problem more. Okay, I think limitations I shouldn't show, right? There are no limitations here, of course. If I'm running out of time, I just wanted to quickly highlight that there are some things that we cannot do with the current setup, with any CPU-based codes in general. So as if you've been following ChatGPT, you know that GPUs are becoming a large thing. And also in astronomy, no matter what simulations we do, we are all wanting to move towards GPUs. And on GPUs, we can sort of get some really, really nice new sort of frontiers to uncover, where on GPUs, for example, we can now resolve not only to AU scales, we can go all the way down to very, very sub-AU scales, reaching almost the stellar scales in terms of the spatial scale. So that means that in terms of the star formation cascade, starting from GMC scales, these simulations can reach the scales directly where you're actually forming your stars. We don't have the physics to actually follow what happens, but then this is the point, right? We can sort of resolve down to the formation of compact metal poor binaries and all these sorts of. And the observational landscape is quite rich. We're getting a lot of things on larger scales, but now as we are starting to move towards smaller and smaller scales, like below parsec with like cosmic gems sort of systems and so on, all of these ISM physics, we need to uncover them and we need to sort of talk about them because they will form large uncertainties in whatever we would infer from these observations. So that's why I have no solutions for you. I just have problems. This cloud scale ISM physics is the cornerstone of the metal poor frontier. And all of these different physical processes and chemistry impact our star formation quite a lot in these environments. And I think one last just thing to mention is that always keep metallicity in the minds if you're making statements or reading statements about the ISM, because a lot of the literature is focused on metal-rich ISMs, and things can look very different in metal-poor ISMs. And I can stop here, so thank you.
All right, questions? Yes.
That was a really great talk. I'm sitting here realizing there's so many things we don't consider in our research and our assumptions. It's crazy. I'm just curious about, like, if this is a uniform metallicity in your clouds, right? Is there, how easy or how hard, I guess, is it to include, like, maybe a metallicity gradient or like a multi out or something like that? Because I feel like that's pretty realistic to have multiple phases of that.
Yeah, no, thanks for the question. It's definitely, yeah, we do not do that right now. We sort of set a metallicity and that's fixed for the entire simulation. It is a bit tricky because then you do want a couple, at these scales, then you're wanting to change your metallicity based on nucleosynthetic yields of the massive stars. And the easiest thing you could do is sort of see but then the problem here is that the masses of the massive stars are not fixed. So you could do it when the stars start ejecting via stellar winds or when they go supernovae, but by then the GMC is gone in a way, right? So that's a bit of a bottleneck there, I feel, yeah.
Thanks a lot for your talk. I was interested about the massive star continuing to accrete after they are in the main sequence. It's true we see in the LMC, the low mass one, but those are clean sequence stars. I mean, once the hydrogen burning starts, it's impossible to continue accrete. So can you say how much that is a result we can trust, or it's a numerical effect? Because, like, doesn't depend on the way you stop the accretion to form a massive star. I don't know the detail. Can you say a bit more about the generacies in the numerical approximations?
Yeah, so the way we are doing the simulations is that once we form a protostar and it's gaining its mass from the surroundings, we update its like stellar temperature and radius based on stellar evolution calculations. So done with MESA or like the Geneva group, for example, and that tells us when will accretion stop or not stop. So if you have a lot of ionizing photons being released, then that's going to push the gas outwards and cut off accretion. But that process sort of seems to be not super effective when we go to very, very low metallicities. So you keep on accreting on these stars, even though they have sort of already reached the main sequence. That's my understanding. So these stars seem to reach the main sequence. If we do like a stellar evolution modeling with the accretion histories of the stars included, we see that they are reaching the main sequence in like 10, 20, 30,000 years. And accretion only shuts off after, if it does, after like 100,000 years or even more sometimes. So at least the first 10 to 30% of the main sequence, you are still accreting. And there's not a lot, especially in dense.
How much do they grow? Is a minimal accretion?
So yeah, so that's the more uncertain bit at the moment. So that's why I didn't sort of get a chance to talk about it. But that's why we have like 3 different cases. It could be that you don't grow at all, which is this case, if feedback is effective at stopping accretion. But sometimes it's not, especially in very dense star clusters. And then you could take any of these tracks and then end up being very, very massive as well. So how often do you go on this track versus this track is something we are not sure of yet, because we need to do more of these simulations. But at least in some cases, you do see that they will accrete on the main sequence.
All right, let's thank Piyush again. All right, next up we have Christy. Go ahead and take it away.
Okay, and we're already counting down. Great. Okay, is the mic working? How are we doing in the back? Okay, awesome. Well, thanks so much to the organizers for the opportunity to share with you today some of the recent progress in the Tempos Optical Survey. If you don't know me, I'm Christy Erba. I'm currently here at Space Telescope Science Institute, but I'll be joining the faculty at Fresno State in a couple of months, and I'll be taking on the directorship of the Downing Planetarium as well. So if you're interested in public outreach or planetariums or massive stars or Tempos, please come find me during one of the breaks. Otherwise, on to our regularly scheduled programming. The results that I'm talking about today in the second half of the talk are unpublished. So if you snap pictures of the slides, please just share them with people that you trust. Thank you. So I usually start talks like this by demonstrating how massive stars lie at the heart of the big picture questions of the decadal. But for today, I get to jump right in because we've already heard a series of fantastic talks describing the importance of massive stars at low metallicity and some of the open questions we have yet to resolve. And I don't think I need to convince you that finding answers to these questions are actually a really important thing for us to do in our developing understanding of the universe. Massive stars are truly cosmic engines, and with the incredible results from first Hubble and now from James Webb, we're discovering just how important massive stars may have been in the development of the early universe. However, the simple fact is that even with the best telescopes today, we can't resolve individual stars at these incredible distances, right? And so we're instead seeing integrated light of galaxies, which is a lot of stars all in one. And so this is one of the reasons why we need to use models of stellar populations that have massive stars as a key input. And I've put up here on the screen several of the variables from massive star physics that get considered in SPS and evolutionary models. I'm not an expert, so I'll take suggestions on the slide. But I do know that these factors are variables that might influence ultimately what we get out of these models. And the trick is, right, that what you get out is only as good as what you put in. And so even models of massive star evolution are highly dependent on the initial constraints that we introduce. So if those constraints haven't been empirically benchmarked, uncertainties can propagate up the food chain, so to speak, and bias our interpretations of ancient populations. So we need to establish the best possible physically motivated descriptions of how massive stars might evolve in metal-poor environments. So as a quick demonstration, this dashed line here on the plot shows a relationship between stellar mass loss and luminosity that's commonly adopted in evolutionary models to predict massive star lifetimes and ionizing fluxes. However, the UV spectra of O stars in the SMC indicate that mass loss rates of these stars could be up to an order of magnitude lower than that common theoretical prediction. And that goes to show that empirical benchmarks really are critical for testing how hot stars behave and evolve in the metal-poor regime. So more to the point, we don't have many available spectra of hot stars in extremely metal-poor environments, by which I mean less than the SMC, so less than about 20% solar. Right? And these are the populations that most closely resemble the conditions we expect in the early universe before successive generations of massive stars had the chance to live, die, chemically enrich their environments. And so to the best of our modern observational capabilities, we have to collect as many hot star spectra in this regime as possible, spanning surface temperatures and evolutionary stages, so that we have a decent population to statistically sample for empirically anchoring our models. So this is as of 2024, and we had FUV spectra of 17 O stars in nearby galaxies in this below 20% solar metallicity regime that were sufficient for this kind of analysis. And as you can see from this plot, the hottest massive stars, which are the ones that contribute to the total ionizing flux production, and then the later O-type and early B-type stars, which are the progenitors of supernova, are missing from what's available in the archive. So the Tempos program was born, right? And this is the treasury of extremely metal-poor O stars. Tempos is adding an additional 12 stars to the COS archive in addition to obtaining new optical spectroscopy of all of its program stars. And from this figure, you can see we've done our darn best to choose targets that fill in the major gaps in this parameter space to provide the best possible coverage within our current observable limits. Just to make that point a little bit more firmly, detailed stellar characterizations are inherently a multi-wavelength problem. And so we want to make sure that we have appropriate spectral coverage to meet our goal of providing those empirical anchors. So we obtained follow-up ground-based optical spectroscopy for our target stars using the 10-meter Keck telescope on Mauna Kea. We also searched through the available archive for UV optical and near-infrared imaging from previous Hubble programs. So we're really looking to provide the most complete picture possible. Tempos is ultimately establishing a new FUV and optical spectral library of O and early B-type stars at sub-SMC metallicities. We're spanning 6 of the nearby dwarf galaxies. They're there on the screen at roughly 5 to 15% solar metallicity. And we are trying to study, ultimately, the analogs of the stars in the early universe. So a quick shout out to Abby Mintz, who I think is in the audience. She published an excellent paper describing the hot star population of NGC 3109 last year. Abby's paper was analyzing the earliest DEIMOS data sets in the Tempos program. And then, as you can see, we have a series of papers in progress. I'm leading the optical ones. There's a survey paper and some additional that will be announcing Tempos in a little bit more detail and describing our initial results from the program. So for the rest of the talk, I'm going to switch gears and tell you about the results from the optical survey of WLM. I think many people here are familiar, but just in case you don't know, WLM is about a megaparsec away, and it's a gas-rich star-forming galaxy with estimates from its nebular oxygen abundance of about 14% solar metallicity. So it's solidly within our extremely metal-poor regime. HST imaging was available in the archive from a combination of several programs. The footprints there are displayed on that image of the galaxy, and we used that to select out the bluest stars at the top of the main sequence for spectroscopic follow-up. So our targets were observed with the Keck DEIMOS spectrograph, and we were also able to obtain additional spectra for 2 of the targets with KCWI, which is an IFU. The DEIMOS spectra are spanning roughly 4,000 to H-alpha angstroms, and the KCWI spectra are about half of that. So I'm showing the blue half right here, so all of the stars are represented. And you'll notice that the spectra are of mixed quality, which will be super obvious on the next slide. This is one of the particular challenges we face in studying individual stars at these distances. The targets are faint, and so instrumental effects and observing conditions can actually be particularly important when we're trying to extract usable spectra. So we reduced these with Pipet, and a quick shout out to the Pipet dev team who helped us resolve a particularly sneaky AstroPy bug. So if you are a spectroscopic enthusiast and you need help, like definitely reach out to the help desks. They are exactly that, very helpful. So our average signal to noise, just to give you a benchmark, is about 20 for the DEIMOS spectra and about 50 for the KCWI spectra. Everything that you're seeing here is rebend to 1 angstrom, and so when we actually get that done, we can boost the signal a little bit, but like, you know, here's what you're looking at. We determined the stellar effective temperature, surface gravity, and projected rotational velocities by fitting our observed spectra, which is there in black, to models from the Potsdam-Wolf-Rayet or power grid for OB stars. We're using the SMC grid that's published on the Power Team's webpage. They also have a sub-SMC grid, and we did test both, and there was no significant difference in the stellar parameters derived from either the SMC or sub-SMC grids. Can talk more about that later. So here I'm showing an example of what this looks like for one of our higher signal-to-noise examples and our lower signal-to-noise examples. The best fit power spectrum is shown in red. The shading indicates lines that were used for the analysis, and the hatching is lines that were excluded or regions that were excluded for various reasons. Suffice it to say, there is an art to working with spectra at a signal-to-noise of about 25. So as I mentioned, we characterized an additional 10 stars in WLM, which allows us to examine its hot star population in comparison to other similarly metal-poor environments. On the left here, we have a relationship between temperature and spectral type, and we consider that because at sub-SMC metallicities, hot stars may have a higher effective temperature than would be expected from their spectral type. The black points are the WLM targets, and then the colored lines on this plot are trends from other similar systems. So the L25 study is Lorenzo et al. 2025 was for a modeled Sexton's A population. M25 in the purple is from Abby's NGC 3109 paper, and the R19 is Varsha Ramachandran's SMC wing paper. So similar-ish environments, okay? And so what we're finding is that the WLM sample is generally in good agreement with this parameter space, but what's not yet clear to me is if this trend is going to shift as we start to analyze the Tempest galaxies that are closer to 5% solar metallicity instead of 15% solar metallicity. So stay tuned. On the HRD on the right there, we've shown the interpolated Bond optimized stellar tracks or Bond tracks for the SMC and Dwarf A models. Again, we're benchmarking the 15% solar metallicity of WLM. And we find that many of our targets are either nearing the end of their main sequence lifetimes or have evolved off the main sequence into a supergiant phase. And what's interesting here is that even though we selected for the youngest blue and hot stars, none appear to be younger than about 5 million years old. And so our analysis suggested that we have potentially 2 binary candidates, which are marked with the X's in the figure based on comparison of their observed luminosities to the luminosities we inferred from the spectral fitting. And we also think that we may have found BE stars. And this is a big question because exactly what the definition of a BE star is depends on the audience that you are in. But I will say these are stars that have evidence of rapid rotation and are B-type stars, and they have emission lines. And I've put the H alpha and H beta lines on the screen. So up at the top here, this is a figure from, if you're a BE star person, the canonical Ravinius et al. 2013 review. And it's showing you what you might expect to see in a line profile for a star disk system at different viewing angles. And I would submit to you that those line profiles of different stars look remarkably like that schematic up at the top. So we can argue this out over coffee, but granted, this is discussing classical BE stars, and we have purportedly rapidly rotating B supergiants with emission lines. So I understand that there's a can of worms here, but we are really excited about the opportunity to follow up on these targets. And we think that at about 1/3 of the sample, this could be a really interesting and significant result for how many BE stars could be found at low metallicity. Okay, I'm going to leave the 30-second summary up here on the screen. Thanks so much for your attention, and I'm happy to take questions.
All right, questions for Christy?
Concerning this BE stars,
Yeah.
couldn't this be BE bracketed stars because you are supergiant, and typically in the Milky Way, these are BE bracketed stars with some forbidden light. So do you see any forbidden light?
We don't see any forbidden line emission. Yeah, great question though. Tomer?
About the BE stars, maybe we can talk later. Specifically, I think that definition excludes supergiants.
Well, the classical one does.
Classical one.
I think from the people that I've gotten advice from, there seems to be 2 working definitions. One is the classical BE star definition, which does exclude supergiants. You have to be a main sequence. And then other is rapidly rotating B stars with emission lines. And so this is where the can of worms gets opened.
But I actually have a different question.
Okay, sure.
When you talk about stars at lower metallicity and being more compact and hot, I think what you would want to compare to are the masses versus temperatures. Like for a given mass, you need to get a higher temperature as opposed to lower metallicity. But here you were comparing spectral types.
Yeah, that's a great point.
I was wondering if you were also looking at the mass versus temperature.
We are, and I don't have that plot available off like right now. I don't have my computer with me. But yes, let's follow up on this in the break.
All right,
I think Christy again. All right, next up we have Sahil.
Thank you. All right, can everybody hear me? Wonderful. All right, so hi everyone. I'm Sahil Hegde. I'm a 5th-year grad student at UCLA, working with Steve Forlanetto, and I'm going to give a quick overview of some of the projects I've been working on thinking about top-3 star formation from a theoretical standpoint using flexible galaxy models. So kind of the driving question that's featured throughout most of my work is this one here, whether we can build and how we can build an efficient model for early galaxies that also includes POP3 stars, kind of with an eye towards these sort of large-scale statistical predictions or forecasts for the signatures of POP3 stars and how we might be able to get a handle on their demographics and properties using population-level studies of galaxies. And I've keyed in on the word efficient here, primarily for the reason, many of the reasons that Piyush highlighted in his excellent review talk just now. And that is to say, given the sort of vast uncertainties in the POP3 theoretical space, we wanted a model and a modeling framework that could really flexibly vary many of these parameters and then follow them through to see how our forecasts for observational signatures would change. So long story short, this resulted in this model which I created, which I've called the ABCD model, or an analytic bathtub for cosmic dawn. And so this is, as is suggested by the name, a bathtub type model or gas regulator model where I'm tracking star formation at the galaxy scale by regulating the amount of gas that is converted into stars and injecting feedback and so on. So I'm going to walk through how this model works and how we can use it to make some observational forecasts. And I think the easiest way to do that is just by looking at a schematic galaxy history. So here, we're going to see a bunch of these plots like this, or schematics like this, where at the left, I'm going to rely on this bathtub analogy fairly heavily, so prepare yourself. And then on the right, I'm going to connect that to a more physical picture of the dark matter halo in green and the gas reservoirs that are at play in this halo. So in red is going to be pristine gas, and then eventually we're going to have some enriched gas start to appear as well. So initially, our dark matter halos grow. We turn on the tap on our bathtub. Water starts to flow out, and pristine material flows in along filaments from the IGM, settles in the galaxy CGM, and eventually cools and falls into the galaxy's ISM, building up a reservoir of pristine gas. This, at the level of our model, manifests as the evolution of a few different mass reservoirs. So here I have the galaxy, or the mass of any of those reservoirs on the vertical axis and redshift on the horizontal axis, from redshift 35 to redshift 5. And here again in green is the halo mass growing smoothly. And then tracking that are the CGM of the pristine gas, and then the ISM reservoir, which tracks that with a slight delay later on. So the halo grows, and the gas reservoirs start to grow as well. And these proceed until the halo crosses the so-called critical mass, at which point a sufficient density of molecular hydrogen has built up such that you can cool, collapse, and form the first stars. So this is like returning to your tub, dipping your finger in to check whether the temperature is warm enough. And then once it is warm enough, then you get in and the first stars start to form. So if we return to our picture, this now introduces our first burst of star formation. And so here, we appeal to some simple estimates for the amount of feedback from the first massive stars that are forming in the cloud to regulate the total amount of star formation that we get from this burst. And this sets basically the normalization of this initial burst. So once we've gotten in the tub and the first stars have formed, you start to settle in, you have a good time, you splash around, and some of the water now starts to fall out of the tub. The stars themselves are also having a good time, and eventually that good time ends, and the first massive stars go supernova, and they too can blow some of the gas out of the ISM into the CGM, and in some of these low-mass mini-halos can also drive gas well out of the galaxy entirely and into the IGM. So for these early star-forming mini-halos, so here the halo mass is around 10 to the 6 solar masses, the potential well is shallow enough that the first supernova events can basically evacuate the entire ISM and temporarily quench star formation with this time scale of the burst here, roughly corresponding to the massive star's lifetime. So in tandem with your supernova event kind of driving gas out of the ISM, you're also starting to enrich the gas. And so you've sat in the tub for a little while, and the water starts to get dirty, and some of that water that you splashed out now builds up this kind of dirty pool around your tub. And so we start to see on the right there these enriched bubbles start to form in the CGM of the galaxy. And so when we return to this picture, now we have analogous mass reservoirs for the CGM in enriched material and the ISM as well. And so this starts to incorporate metals into our galaxy and starts to transition us away from being in the POP3 dominated phase. So these metals, this dirty water, starts to mix with all the water that you've splashed out of the tub. And eventually you start to build up this more dominant metal enriched reservoir in the CGM. And that material ultimately starts to fall back into the ISM, settle down, and is able to form a more dominant star-forming disk. And so here we can then trace how that happens with both POP3 and 2 stars, and we get this kind of evolving series of star formation cycles, or bursty cycles of star formation, which result in evolving ratios of POP3 to 2 stars. And so here I've cut this off at around 270 million years, once reionization starts to play an important role here. And now we need to think some more about environmental effects. So here we've been in the tub for about, like I said, 270 million years. And so now it's time to pay the bills. And that is to say, if you've had your water on for that long, your water company is going to come calling, and you gotta pay up. And so for our galaxy on the right there, that means that as the first generations of stars have formed, they've started to ionize the local universe, and along with that ionization have started to heat up the IGM. And as the IGM gets heated, that can suppress accretion into the lowest mass halos, thereby kind of quenching their star formation in effect. So what that means is that we trace this sort of accretion threshold, which starts to build up as the first bursts of stars form. And if we revisit our picture, you can see that quantitatively we now have different amounts of gas available for star formation in these two reservoirs, and resultingly different masses of stars that form for this fairly low mass halo. That's around 10 to the 8th solar masses at redshift 15. Along with that external feedback from reionization, we also, in addition to having your punitive water company, maybe you also have a terrible plumbing system in your house. And as the dirty water starts to drain into the tub, maybe some of it starts coming back out the tap. And so what happens in this case is that we start to see some metals or enriched material flowing in along the IGM. And now this is in effect sort of suppressing the level of pristine gas buildup that we have and the amount of pristine star formation that can proceed. So in our picture, we can now finally complete it, and we see that at the very latest times, as the IGM starts to build up, and as the metallicity of the IGM starts to build up and the volume filling fraction of metals grows, then we start to get a suppression of the pristine reservoir and a quenching of POP3 star formation at the latest times. So this was for one halo of one particular mass, and this is us solving a set of differential equations to model this halo. But we can do that for a variety of halos of different masses. So here I'm showing the 3 different line styles, halos of 10 to the 11.5, 9.5, and 8.5 solar masses. And I've just isolated their star formation histories here. And you can see how we get quantitatively different star formation histories for those halos, depending on how these feedback effects interact with the halo and the gas reservoir that it has available. We can integrate over those histories and ultimately can see that at the latest times where JWST is observing galaxies in the epoch of reionization out to redshift 15, if we look at the star formation rate density, it's really dominated by, pristine star formation is really dominated by star formation in the most massive atomic cooling halos. So we'd be kind of more incentivized to look for these pristine stars forming at the more massive end, as Emma mentioned in her talk yesterday. So we can actually take these kinds of theoretical predictions and we can change gears and talk a little bit about large-scale observational signatures. And here, rather than thinking about galaxy surveys in the way that a lot of us have been talking about thus far, I wanted to highlight a different observational strategy, and that is line intensity mapping. So this is basically the practice of, rather than looking really deeply at one galaxy and trying to study its ISM properties in detail, you look at a very coarse, low spatial resolution map of galaxies in emission all across the sky, and you measure the aggregate emission from all of the galaxies in your survey. So this includes the faintest sources, which may be those POP3 star-forming mini-halos. So then the question is, what line do we choose to study? And here I'm going to appeal to a line that should come as no surprise, which is to say the helium-2 1640 angstrom recombination line. And so here I'm just demonstrating that we can translate our star formation rate densities that we get out of our models on the left to mean intensities in helium-2 in red and H-alpha in green on the right. And this just kind of makes the point that the POP3 stars forming with a more top-heavy IMF will dominate the mean intensity of helium-2 across the sky for all the way down to redshift 5. But we don't just have to investigate the mean intensity of this line emission across the sky. We can actually also think about fluctuations in that line emission, and so spatial fluctuations in that. And we can measure the line intensity power spectrum. And so these are examples of that power spectrum measured for H-alpha in the solid line and helium-2 cross H-alpha in the dashed line for 3 different variations of POP3 parameters. So the POP3 star formation efficiency here on the left, the IMF slope in the middle, and the peak mass or characteristic mass on the rightmost panel. And so we've built this framework that's kind of flexibly able to vary the POP3 parameters and forward model some of these variations in the line intensity power spectrum. And then we can model how this actually feeds into some realistic observations. So I'm going to briefly just demonstrate how, if we were to take a next generation line intensity mapping survey, like here I'm looking at the cosmic dawn intensity mapper CDIM plus, and I'm exploring how we can learn about POP3 star formation from different observations. So here are those same 3 parameters and Fisher forecasts for the constraints that we could get on those parameters by measuring H-alpha alone. If we were to fold in, if we were to measure just the cross power between H-alpha and helium-2, we get slightly less constraining power because of the weaker signal, but we get some more sensitivity to the IMF. And we could combine those 2 together, and we could, in principle, get some really tight, nice constraints on POP3 demographics, and we would be able to maybe distinguish between different POP3 models. So this is kind of a proof of concept, and this is like a next generation type view into what we might be able to do in the POP3 regime with intensity mapping. But as I move to my conclusions, I do want to highlight that there is actually some limits on POP3 that we could potentially place using intensity mapping experiments that exist today in tandem with Galaxy surveys, such as JWST and those that'll be carried out with Roman if we use Sphere-X. So I'm happy to talk more about that, but I'm just going to leave the conclusions up and take any questions. Thanks.
Questions?
Great talk, by the way. Yeah, thanks for this. I'm just wondering, so my understanding is a lot of times regulator models will have a series of free parameters. So I guess, like, how do you, do you have a lot of free parameters? And if so, how do you choose or calibrate those?
Yeah, so that's a great question, and it is true that these types of models, in order to remain efficient, do rely on choices for free parameters. And I think one of the reasons why I tried to build this framework so flexibly was such that we could make choices for free parameters that are inspired by simulations that work in different regimes. So at the smallest scales, thinking about star formation efficiencies or how feedback couples to the gas, and then we can see how those feed through all the way to the population level metrics for how much POP3 star formation we get and what epochs we expect to see it in. And so the answer is that we choose some fiducial set of free parameters. There aren't a huge number, but there are some in our model. And we, by virtue of it being a fairly simple model, we can kind of directly trace how those parameters modulate the population level amounts of star formation. So, yeah.
I apologize if I missed this or it's a naive question, but how in this mapping do you distinguish between POP3 and other sources of helium-2?
So that's a great question, and it's true that there are other confounding variables in doing a mapping of helium-2 across the sky. And so I would advocate for intensity mapping as a way to maybe take a census of all the helium-2 emission that you could see at any redshift that your instrument is sensitive to. So really, ideally, if you could go to super high redshift with a next generation intensity mapping survey, then you would be sensitive to where we might expect POP3 stars to be the dominant source. In our estimates here, I've just kind of tried to estimate the helium-2 contribution from Wolf-Rayet stars, so based on some observational scalings, and then used some theoretical models for POP3 to quantify just how much more dominant they are. But it's also true that you will get different signatures from AGN and other hard ionizing sources. So I think one way that you can kind of get a handle beyond just what I've shown here in measuring the sort of aggregate helium-2 power spectrum is if you look for signatures in the power spectra that correspond to star formation in particular regimes. So this like wiggliness of the power spectrum corresponds to a specific feedback effect that only affects very low mass halos where we expect POP3 star formation to be the dominant mode of star formation. So if you can see those wiggles, it would be really cool for a variety of cosmological reasons, but also that might be a signpost that you're seeing star formation in these halos where POP3 would be dominating.
All right, let's thank our speaker again.
Where is it? Got it. Okay.
All right, up next we have Alejandro, so go ahead.
Hi, everyone. My name is Alejandro Olvera. I'm a fifth-year PhD candidate at Arizona State University. And today I'm going to talk about my work using star-forming galaxies, or star-forming regions within galaxies, to trace ongoing gas accretion in nearby galaxies. And this is work that I've done with my advisor, Sanch Bothakur, also at ASU, as well as a lot of other people that you see listed here. So we just heard a really great talk that showed that galaxies exist in this ecosystem where gas flows in and out of the galaxies quite a bit, out because of feedback and things like that, and in to support further star formation in the galaxies. It's been shown that galaxies have depletion times between 1 and 2 gigayears, so in order to sustain star formation for longer than this, they need continuous supplies of gas flowing into them. So obviously it's an important process, and so there's some questions that we could ask. How does the gas from the CGM or the IGM reach the inner disk, and how does this fresh gas affect the kinematics and the metallicity within the existing ISM in the disk? However, these questions have been answered a little bit through theory and simulation, but observational evidence to try to answer this is a little bit lacking because the accreted material is quite diffuse, making it quite hard to actually observe. One method that has been used to indirectly trace these inflows is by looking for radial flows within the disk of a galaxy, so gas moving in or out from this, relative to the center. And this is typically done on H1 data where they model the disk as a tilted ring, typically concentric rings. And you can do this with something like Fourier decomposition or 3D Barlow. And people have typically measured that the radial velocities within galaxies are on order 10 kilometers per second, plus or minus 5 potentially. And that's kind of across the entire disk. Another way you can trace inflows is by looking for star-forming regions. If you have this CGM cloud that's, you can assume metal poor, it can accrete into the galaxy somewhere or another. It can then dilute that existing star-forming region and bring down the metallicity relative to the expected gradient. So here you have to know that there's some sort of metallicity gradient, and this region will stick out varying degree. Regions like this were first titled anomalous low metallicity, or ALM, H2 regions in the Swang 2019 paper, where they essentially used a metallicity offset from expectation from a mass metallicity relation, and found that there are some regions that are offset by a bit. Interestingly, these regions have also been found to have a higher N/O ratio relative to O over H. And traditionally, these regions have offset from the expectation between 0.1 and 0.3 dec. And here's some other studies that have looked at those. So in order to look for these, we looked for these in a sample of nearby galaxies from the deciphering interplay between the interstellar medium stars and circumgalactic medium survey. or DISC. It's a multi-wavelength survey that combines high-resolution VLA data to look for the H1, quasar absorption spectroscopy to look at the CGM with HST, and then the stellar continuum we get from the Vatican Advanced Telescope in Arizona. And the part that I contributed to this survey is getting multi-object spectroscopy in the optical of the star-forming regions within our galaxies. Our galaxies are pretty face-on, most of them. They're L-star galaxies, they're very nearby, and they're all detectable in 10^1 centimeter. And so with that, this is the 11 galaxies I've observed, and I got over 550 regions observed in each of these galaxies. And you can see that they're scattered all throughout the disk, and we're primarily also interested in the outskirts of the disk where the inflows might be occurring. This is an example spectra of what you might get for one of these regions. And with that, we pull the fluxes from H alpha, H beta, O3, and 2S2, the typical strong lines. And we measure metallicity, particularly going forward, I use the N2 index to measure metallicity. And so with all these regions, you can form a gradient and look for these anonymously low metallicity regions. So I'm showing the gradients here for each galaxy. You see a mixture of flat and negative. But interestingly, I'll highlight that there are these outlier regions that we believe are these ALM regions. And you can see that they're to varying degree lower in metallicity. Some are dramatically lower, like in the case of 3351. Others are close to the gradient, but still outside or within the 5 confidence interval of the line fit. And so we believe that many of these regions are created by some sort of inflow from the CGM or the IGM. And this is some preliminary work that's still ongoing, but we can try to characterize some of these ALM regions and backtrack how much mass might be needed to bring down the metallicity to the observed relative to where it should be for the expected from the gradient. And what we find is that the mass that needed to dilute that by that amount is actually similar to, this is in log, that of HVCs around the Milky Way. So this is potentially revealing a pathway for how some of these regions might be occurring by this vertical inflow of like high velocity clouds. So that's interesting. We also find that a lot of them are within the R25 of the galaxy as well. You might expect maybe they might be further out, but they're actually kind of in the middle of the disks itself. We find that roughly 5 to 7% of the star-forming regions we observe are these ALMs. One caveat is that I talked about using the radial gradient to find these. You can also use the mass-metallicity relation. Sometimes they agree in it being an ALM, sometimes they don't, and so that's something I'm going to explore in this paper. And so now I'll turn our focus to one galaxy in particular in the sample, NGC 3344, with this beautiful HST image here, and ask the question, what is diluting the H2 regions? Can we find any evidence for that? Because before it's just like a theory saying that it's probably from inflow. NGC 3344 has an extended H1 disk, and allowing us to measure radial velocities. It's also a type 1 extended UV disk that has an extended UV emission beyond just the normal optical. These types of galaxies exist for 30% of star-forming galaxies in the local universe. And I have detected 6 ALM regions within the XUV disk of the region, so of the galaxy. So those are the 6 that you see right here. I highlight them on the thing. So we know that those are anomalous in metallicity. And then we can turn to the high resolution VLA data. It's about 6 arc seconds in resolution, which is pretty good for radio. And model it with 3D Barlow, the tilted rings, and backtrack out some radial velocities. And so you pay attention to the cyan points here. They're showing the radial velocity for the orientation, rotation of the galaxy. Positive velocities indicate gas moving away from the center, and negative velocities indicate gas moving towards the center. And what you see is at the onset of the XCV disk, around 6 kpc, you measure average radial velocity of -7 kilometers per second, and that negative value extends all the way out to about 10 kpc. And at that same location is where we observe these ALM low metallicity regions. And so together, it can potentially paint up another pathway for how these might be formed. This metal pore gas can accrete onto the outermost parts of the galaxy. And then, due to losses in angular momentum, move in and affect and dilute the metallicities of some star-forming regions in the outer disk. and lowering them down and supporting further star formation. And so this is a work that I've recently submitted. It's also one of the first times that anyone's ever connected the radial velocity information with the observed drop in metallicity as well. So it's a really interesting result. And I see I have some time, probably spoke a little fast. So I can go over this slide. There are still some open questions I've been thinking about a bit of what is the underlying stellar population of these specific low metallicity regions? Are they also low in metallicity? If so, how low are they? Do these regions exist at higher redshift? We heard a little bit about cosmic noon, but what about beyond that? And are the ones at cosmic noon the same as this? And how big are these regions? It'd be really nice to get some IFU data to really map out the full star forming region, and then we also get a better handle on the mass of them as well. And this is not an exhaustive list, and given the times, shameless plug that I will be on the job market next fall. So if you are interested in this work, or you have a upcoming postdoc application or position, I'd be down to chat. Yeah, so I'll leave you with my results here. These low metallicity regions are a really good tracer of inflows. It's a observational way of tracing gas inflows. And this is the specific study, NGC 3344, which is applicable to about 30% of galaxies. We find that these radial gas motions are what's bringing in this low metallicity gas from the outer parts of the disk. So I'll leave it at that and take any questions.
Questions? Danielle?
So I'm always a little bit wary of N2 strongman abundances.
Yeah.
I was wondering two things. Like you said, you did O2 and O3, so I was wondering what your R23 or such look like. And I was also wondering what the ages might look like of these different regions, either just from like a Balmer equivalent width, like a Balmer line equivalent width, or combining with infrared data to look at older stellar populations as well, if there's relations there.
Yeah, the N2 question is a good point. I've cross-checked it with O3 N2, and the scatter and the gradient increases sometimes for most of the cases. And a few of the regions that are very close to the edge of being considered ALM in the radial gradient do go away. But for the most part, some of the strongest ones are still there. So it's.
What about without nitrogen, like R23?
I haven't tried R23. Yeah, that's something I can try.
I would love to hear what you get.
Yeah. To the other question, the ages. That's something I'm also interested in myself. We actually recently submitted an HST proposal to try to get the stars, and we'd be able to constrain the ages a little bit more with that.
Hey, thanks for the nice talk. So if the gas is kind of funneling in and lowering the metallicity and supporting more star formation, you might think that these might be some of the most luminous H2 regions in these galaxies. Do you see that these are outliers or towards the top of the luminosity, H beta luminosity function or something in these sources?
Yeah, it's a really good question as well. I haven't necessarily done the numbers, but visually looking at the regions in the map where they do tend to be very bright. Yeah.
Okay, yeah. And then, if they're bright, this might help, but some of these galaxies have a lot of archival deep spectroscopy. I don't know if there's any overlap in the TE-based metallicities with some of the regions you've selected, but it'd be really interesting, of course, to confirm their true low metallicity nature with the correct method.
Yeah, some of them have some really good FANGS data, but a lot, which is good because you have IFU from Muse, and a lot of lines. But the problem is a lot of that data is in the center, and a lot of these are kind of right on the edge of where that data stops. So. Okay. We need more imaging in the outskirts of galaxies. That's my argument here.
And I was wondering, are these, you didn't show where they are located.
Yeah.
Is it one side of the galaxy, and then overall.
It's random across the galaxy.
So is accretion coming? Because I was thinking it's coming via filaments, or you see.
I think it's a mixture of both things occurring, right? Because at some points I said like for 3344, like these radio flows can help, and so that's more of like a ring. There might be a ring if you very simplistically assume it's a ring. That's like pretty low in metallicity, maybe. But then there also might be cases where these HVCs are falling in specific regions. Yeah.
All right, let's thank our speaker again. Reminder that you can still ask questions on the Slack channel underneath the threads. So next up, we have Zihao.
So hello everyone, I'm Zihao Li from University of Copenhagen, and I'm a PhD student right now. And I'm going to talk about some POP3 star formation and galaxy overdensity. So the first question is, where should we look for a POP3 formation? So the theorists predict that the POP3 formation starts at the very early time in the universe, maybe higher than redshift 10 or 20. So at that redshift, it can be too difficult to be detected directly with James Webb. So there's another scenario that the POP3 formation can be delayed late into the epoch of reionization, or even down to redshift 3. So we can probe the late POP3 formation at relatively lower redshifts. So there's another complementary detection method that we do not detect the POP3 stars themselves. We can detect their relics in terms of metal absorbers, because of the galactic outflow can drive those POP3 star ejecta into a larger radii. So we can detect those metal absorbers to see if we can find any signatures of POP3 formation. And the question is, what is the host of those POP3 formation? Are they in very massive galaxies, or they are in very low mass star clusters? So we can use those metal absorbers to probe that. So in this study, we use the XQR30 catalog and combined with James Webb Grissom observations. So from the based quasar spectroscopy, we have a large metal absorber catalog, and we can use those abundance ratios to see if their enrichment pattern are consistent with POP3 formation or not. And after we selected those metal absorbers, we can use the James Webb observation to directly map the galaxies around the absorber redshift. And we can study the correlation between the metal absorber and the galaxies. And here we are using the two quasar surveys, Aspire and Aegir program. And there's a large sample of galaxy catalog. And we cross-match it with the metal absorber catalog. And we find some interesting results. So from this observation, we find one metal absorber with abnormal metal enrichment pattern. The silicon to oxygen ratio and the carbon to oxygen ratio is very high. And some theorists predict that this kind of abundance pattern should be produced by POP3 core eclipse supernova. And what is also very interesting is that at this metal absorber redshift, we observe a large galaxy overdensity, about 17 member galaxies at the same redshift. So what's the correlation between this POP3-like metal absorber and the galaxy overdensity? And then we measured the metallicity of those member galaxies in this overdensity. We find this galaxy overdensity is an outlier compared with any other galaxy overdensities. For example, there are other three galaxy overdensities along the same quasar side, but their metallicity is much higher than this one with POP3-like metal absorber. And there's another metal absorber without such POP3-like abundance pattern, and this galaxy overdensity also has a higher metallicity and consistent with the mass metallicity relation at the same redshift. But for this protocluster with metal POP3 metal absorber, so the metallicity is like 0.4 dex lower below the mass metallicity relation. So this is quite an interesting system. So this environment might be a very chemically primitive environment, and those POP3 formation can be favored, and those metal ejecta from those POP3 stars can be well preserved in such a primitive environment, and it should not be mixed with other POP2 supernova ejecta. So we can see the POP3 signature in this environment. So another question is, what is the host halo mass of POP3 formation? So with this protocluster, we can actually measure the cross correlation of metal absorber and the surrounding galaxies. So when we do the cross correlation and we fit it with the halo occultation model, we can constrain the halo mass of the POP3 absorber. So we found that the best fit model supports a halo mass like above 10 to 11, a bit with very large uncertainty, but we can set an lower limit of this host halo mass, like above the 10 to the 8. So that is the typical threshold for atomic cooling halos. So from this observation, we can actually constrain that the POP3 formation at this redshift should be inside the atomic cooling halos instead of lower masses halos, like lower mass mini halos. So the other thing we are investigating is that what boosts such POP3 formation in such an environment. So also from the quasar spectra, we find an interesting Lyman alpha transmission peaks around this absorber. So those peaks suggest that this region is partially ionized, so we can say exists Lyman alpha transmission. So this large-scale environment should be under a certain amount of ionizing radiations. Such a radiation could boost the POP3 formation, as suggested by some theorists. So the Lyman-Werner radiation from those galaxies potentially boost some POP3 formation among this environment. So here is the scenario we are thinking about right now, such that because all of the member galaxies are identified through O3 emission lines, so they cannot be real POP3 galaxies. However, we indeed detected some POP3 supernova signature, so there should be some POP3 formation in this environment. So it cannot be directly inside those galaxies. It could be outside of those galaxies at large radii from the central galaxy, and this radiation could boost the POP3 formation away from the central galaxy. So there's an interesting analog. So the recent discovered the helium-2 emitting clump from JWST. So some theorists also suggest that those helium-2 emission could be boosted by the Lyman-Werner radiation from JWST, and there is some POP3 stellar clumps, and they produce such helium-2 emission. So this could be a possible scenario for our observation as well. Yeah. So there's the summary. So we identify a very metal poor protocluster, and along with the POP3-like metal absorbers. So the absorber has a very high carbon and silicon abundance that is consistent with POP3 core eclipse supernova. And the protocluster is chemically primitive, and they might preserve in POP3 enrichment signatures. And it also suggests that pulse wave formation might consist to happen down to redshift 6 in the outskirts of massive halos. And this method can be a very promising way for us to probe more similar systems about pulse wave stars. But there are also some caveat in this study. So the galaxy metricities are only based on near-Gaussian observations. So the real metricity should be conferred by near-spec observation in the future. And the pulse wave model, we will rely on pulse wave model. So it's not necessary that the high carbon or silicon abundance is produced by pulse wave stars. There are other channels such as Wolf-Rayet stars or very massive metal pool stars, as you have talked about a lot. So this pattern might not be unique for pulse wave stars. And also we do not directly detect the pulse wave stars or pulse wave sensitive emission lines such as helium-2 in this study. We are only probing about the CGM metal absorbers. So in the future, we would like to propose some further observations, such as we can use deep IFU-like spectroscopy to search for the large surroundings around this absorber to see if we can directly probe some pulse wave signatures that like helium-2 clump or metal line-free clumps. And this is a very single system. So we infer a halo mass of pulse wave host halo, but we need a larger sample to do a better statistics and to see if the pulse wave absorbers preferentially reside in metal pool of densities or not. Okay, thank you very much. I'm happy to take your questions.
All right, questions?
So when you have calculated the ratio related to abundance ratio, did you correct for the dust depletion for this?
For the ratio, what's the question?
Yeah.
Yeah.
Did you correct for the dust depletion of silicon or carbon? The dust correction, did you do the dust correction for these values?
Dust correction. No. We use the observed.
Potentially move your point to that way.
Yeah, if there's dust, it can move towards it, yes. Yeah.
One more question is, what is the ratio for the quasar?
The ratio for the quasar, ratio of 6.3 around 6, but yeah.
Very cool result. What are the typical velocity offsets between the absorbers and the emitters?
Velocity offset. So you mean for individual galaxies or the whole scale?
So if you take the absorbers and you take the redshift of the absorber and the redshift of each galaxy, you're going to have something 200 kilometers per second, or like what is?
Yeah, so for the closest, it can be very close, like hundreds of kilometers. Yeah, that's the closest galaxy, but there are also other galaxies. Yeah.
Oh, I see. Okay.
Yeah.
Okay. Well, then I have no one else. Go ahead.
So I do not understand. How did you infer the mini halo part? Like you took the cross correlation and the halo mass that you actually infer is the halo mass of the over density itself, right? Like the minimum halo mass 10 to the power 11. Is a typical halo mass for
you mean?
over density. So this is,
Yeah, there's a halo.
I didn't understand this part. How did you infer that it was an atomic halo or?
Yeah, we cross correlate the central metal absorber to the galaxies. So we know the halo mass of galaxy. So when we do the cross correlation, we can also infer the halo mass of the absorber. It's the absorber host halo. Yeah, not the over density.
All right, let's thank our speaker again.
It's this one.
All right, hello everyone. My name is Alexandra Masigan, and I'm a PhD student at Columbia University and the American Museum of Natural History, and I'm going to be talking about the relationship between the binary fraction and metallicity, which has already come up a lot. So I will remind you very briefly that close binaries are quite common. If we plot the binary fraction as a function of stellar mass, we find that for stars around the mass of our sun, 50% of them have a binary companion. And that fraction only goes up with mass to almost 100% for the most massive stars. This is important because these stars aren't just coexisting. A lot of the time they are interacting. So if we look at those O stars, for example, less than a third of them live out their lives as effectively single stars. The others are transferring mass, merging, and interacting in ways that fundamentally alter the outcomes of stellar evolution processes. This chart shows all of those possible outcomes, but what I want to highlight here is that a lot of these outcomes and intermediate states are very astrophysically interesting. So for example, if you care about binary black hole mergers, which are gravitational wave progenitors, or if you care about type 1a supernovae because you're interested in cosmology and standard candles, these are things that are produced in binaries. These are not things that we can understand just by studying single stars. So it's important to understand how the binary fraction changes with environment. And for our purposes, we might ask specifically, how does it change with metallicity? If there is a trend, that means that these outcomes are evolving with cosmic time, which is something that we would want to know. We can summarize our current state of knowledge on this topic by breaking it into two regimes. At the low mass end, there's pretty strong evidence that there is an anti-correlation between the binary fraction and metallicity across a wide range. So this is for solar type stars. This is from Mo et al. 2019. And another important finding of this paper was that when you're doing this type of study, you have to be really careful to account for your survey incompleteness, so which binaries you aren't observing. By doing that, he was able to unify 5 studies that use different techniques, different samples, to agree on this result. And that will come up again in a second. Then at the high mass end, things are a bit less certain. So we have older work, also by Mo, that looked at eclipsing binaries in the Magellanic Clouds and found that there didn't appear to be a dependence on metallicity for the OB binary fraction. But more recently, we've had other studies that have revisited this topic. The binary at low metallicity, or Bloom survey, has already come up a few times. And the results coming out of that survey are starting to call this into question a little bit. So first we have their O-star results, which found that there does not appear to be a statistically significant trend with metallicity, though I will note they can't rule out an anti-correlation that is on the same order of magnitude as that for low mass stars. More interestingly, perhaps, is their B-star results, which did find a statistically significant anti-correlation. So this is in direct tension with that earlier Mo result, and this just really highlights how this is still an open question, and we aren't really there yet when it comes to understanding how binary evolution changes across cosmic time. So my own work has also been focused on the Magellanic Clouds, which I don't need to tell you have very different average metallicities. We're at half solar metallicity in the LMC, 0.2 in the SMC. And the goal was specifically to do a relative comparison between these two so that we can avoid a lot of those nasty completeness effects. To do that, we conducted a survey with the dark energy camera of one field in each galaxy. We detected about 2.5 million unique stars in each field. This was a high cadence survey. We took observations every 5 minutes. There was also short baseline. We observed over 2 nights in the LMC and 4 half nights in the SMC. So I have some example light curves here, but what I want to highlight is just that we are limited in our detectability to the shortest period binary systems there are. To find the binaries, we first trimmed our original sample down to a high quality subset, which reduced it substantially to about 400,000 stars. At that point, we calculated some variability statistics. Where necessary, our thresholds were dependent on magnitude because obviously things like RMS increase on average as you go to fainter stars. So we took that into account. And by applying these cuts, we narrowed our sample down to about 70,000 variable candidates in each galaxy. At that stage, we conducted a search for periodicity using the Lom's-Gargle periodogram. We limited our search range to 0.1 to 2 days. Very short, but again, we're working with very short baseline data. I'm going to skip over a few of the details here for time, but I do want to highlight that once we had measured the periods, we were able to fit Fourier models to the light curves in order to measure morphology parameters. So descriptions of their shape, which ended up being helpful for classification. We also took advantage of the Ogle catalog of variable stars. We had about 2,000 sources in our LMC dataset and 1,000 in our SMC dataset that matched to labeled short period variables in the Ogle database. And you can see that the eclipsing binaries, our targets, which are shown in green, are very nicely separated from other short period contaminants like Cepheids, RLI rays, and Delta Scuti in color magnitude space with a very simple cut. So we took that cut. There is still some contamination, particularly on this side with the RLI rays. So we also used a morphology parameter called phi21 to further refine the sample. And that's what's being shown in these histograms on the bottom. Again, the colors correspond up there. So you can see that the green eclipsing binary histogram is very nicely centered at 0 in this space, which just represents the asymmetry of the light curve. We expect that eclipsing binaries are fairly sinusoidal. Pulsational variables have this sawtooth light curve shape, so this separates them nicely in addition to the color magnitude cut. So those two cuts became the basis of our selection, along with a few other things related to the quality of the best period. And that brought us to a sample of about 500 binaries in the LMC and 350 in the SMC. So there are more binaries at high metallicity, right? No, we have to account for incompleteness. That's what we learned from Mo. We can't just take this at face value. So to do that, we ran injection recovery simulations. We took non-variable light curves from our data set, which encode our typical cadence and noise properties. And then we took empirical binary templates from the Ogle database, assigned them some period and amplitude, injected them into our real data, and ran them through our pipeline to see if we would recover them. What I'm showing here is the results of that in two magnitude bins. So we have a brighter one on top and a fainter one on bottom. The x-axis in all cases is period. The y-axis is amplitude. And the red points represent our candidates. So one important thing to note is the simulations here are being binned by their observed rather than their actual parameters. We don't always sample the full amplitude of a light curve or get the correct period. Sometimes we record half the period. So that captures the effect that's happening both in our real data and with these simulated. In each cell on this grid, we're calculating the completeness as the fraction of simulations that are recovered by our pipeline versus not. And from that, we are able to calculate binary fractions using this formula. If we assign n to be one of these red points, so a specific binary, then we take the completeness in the cell that it's landing in, C, and we divide 1 over C. And the reason for that is if C is 50%, you're missing one binary for every binary you detect, so you should be counting 2 binaries in that cell. We sum that up over everything, all of our candidates, and we divide by the total number of stars in that magnitude bin. And this gives us a binary fraction for both the LMC and the SMC. And we then take the relative ratio. We divide SMC over LMC so that we don't have to worry about all the finicky things that go into calculating exact binary fractions. That gives us this result here. So I have SMC over LMC on the y-axis. If it's above 1, that means there's more binaries in the SMC, more binaries at low metallicity. If it's below 1, it's the opposite. And I've binned it by magnitude here to make sure that the numbers are sufficient for calculating the statistic. These are the numbers. But if I label these by spectral type, you see that we're covering a pretty wide range from B down to G. And I want to point out a few things about this plot. The first, maybe more mundane one, is that like the Bloom survey with their O stars, we have this big error bar on our results at the high masses. So the mean is above 1, which suggests that maybe there are more binaries at low metallicity in the SMC, but we can't actually rule out the fact that we are consistent with parity between the two galaxies in this regime. But the more interesting thing is the fact that when we get down to this low mass end, it's flipping the other way. We actually see more binaries in the LMC, which does appear to contradict Mo's result. So how could this be? Well, one thing to point out is that, remember, we are operating at a very short baseline for our survey. So this population is likely dominated by contact binaries, which is an evolved state of close binaries. Specifically, you start with 2 stars that are not in contact, and then you have to lose angular momentum in order to bring them into contact. And we think that the dominant mechanism for this is magnetic braking, which we also expect to be more efficient at higher metallicity. So it's possible that even though the progenitors of contact binaries might be less common at higher metallicity, because magnetic braking is more efficient, we are actually seeing more of these things in the LMC and the SMC. All right, I actually talked really fast. I'll put up my conclusions and just say these couple points. So overall, we did find that there's seemingly no relationship for these higher mass stars, though TBD, we can hopefully boost the numbers somewhat. But we have this result at the lower mass end of things where the ratio is significantly less than 1, which is surprising given our expectation that the binary fraction should be anti-correlated with metallicity. But I do want to remind again of this caveat. We might not just be probing primordial binary formation here. We are probably also probing evolution of these systems, mass transfer and magnetic braking and all that good stuff. And disentangling that is going to require a bit more work. Thank you.
Questions?
Oh, sorry.
Really nice talk. So obviously you have this really short baseline. But like I don't know enough about the DCAM survey and like the future of that. But like, what are you expecting to be able to probe longer baselines with forthcoming data?
So I just showed this to my advisor a couple weeks ago, and he said, wow, we can go ask for more data now. Okay. So yes, from my understanding, since the main survey is over, there's more time available, and we're hopefully going to be able to go back and do this more robustly.
Cool.
Yeah.
Very nice talk, very cool results. I will not talk about the cadence, but I was wondering, so when you showed like where you put the camera too, in SMC you put it at the lower part of the wing, so I was wondering if this might introduce some biases that you get in the binary fraction.
Yes, it's a good question. So these fields were selected. I was not involved in the process, but I was told that they were selected in order to ensure that there are very similar stellar densities. And then I made this plot and I said, are we sure about that? But we do end up with similar numbers of detections, at least, good detections in both frames. So I have been taking that at face value. I think it's a great question. We are avoiding like the 30 door region of the LMC, but we're definitely in an area that is closer to the bar. So it definitely could have an effect, and I haven't explored that in detail yet. Yeah.
Hi, really nice results. If I'm not mistaken, the results you showed us in the end rely on not per se on your observed population, but on the bias corrected population.
Yes, right? That's correct.
So I was wondering how bias dominated you are here and how strongly the bias correction process impacts your conclusions potentially.
Yes, great question.
Whether you have any insights on this.
Oh my God, it's so slow. I'm sorry. There we go. Okay, yes. So how strongly biased are we in this regime? Well, so we kind of see this from the raw numbers. The correction does seem to operate more strongly in the LMC, I believe. I'm sorry, I don't actually have any plots that could show this quantitatively. But because we have such small numbers, we are decently bias dominated. So it is impacting the results, and we need to make sure that we're careful about it, which is what we've tried to do. I'd be happy to talk more in detail about it after. Yeah.
Right. Thanks for the nice talk. So I was wondering if you have any expectations on the wide period boundaries that should exist in these metalicities, and are there more or less in number than the previous metalicities?
Yeah, good question. I wish I had a better answer than to say we avoided them like the plague, because the sensitivity there is so bad that there's just no way to be confident in our completeness correction. I mean, we would have to get lucky enough to catch a fraction of an eclipse or one eclipse, but then how do we know what the period is? So we were very deliberate in selecting against those, and I would have to say the only expectation I would have is that it should follow the results in Mo et al.'s paper. That would be something that longer cadence could help with. It's also something I'm interested in trying to mine out of this data set, but it would be a lot more uncertain, so I can't really say anything. Sorry. Yeah.
All right, let's thank our speaker again. All right, next up we have flash talks, so if our speakers can come.
Okay, hello everyone. My name is Kevin. I am a first-year PhD at INAOE in Mexico, where I work with Dr. Yaledi Bakaramaya and Dr. Roberto Terlevich. Star forming complexes such as low-metallicity giant H2 regions host a variety of stellar populations. In a previous work, we studied the resolved and more extended stellar populations of these regions using HST images. And we determined that the star formation has been ongoing for approximately 20 million years. We also found that these regions contain compact unresolved cores that can be detected only in JWST images, some at wavelengths longer than 3 microns. Using MIRI images, we were able to detect these embedded and younger star populations within these regions. We performed PSF photometry on HT and JWST images, covering a wavelength for 400 to 25 nanometers to 25 microns in order to get the fluxes of these regions. We didn't perform the convolution of these images to bring them to a common resolution in order to avoid contamination for neighbor clusters. In this way, we construct the SED of each source, and we fitted models using SIGAL to derive the physical properties. The ages of these clusters are younger than 3 million years. Meanwhile, the extinction values are very high. For the sources of NGC 5461, the values are high as 40 magnitudes. Meanwhile, for NGC 5471, the extinction is high as 20 magnitudes in the B band. With respect to the stellar masses, they are in the range of 10 to the 3 to 10 to the 5 solar masses. These observations suggest that the star cluster formation can persist even in this kind of environments that are affected by considerable feedback from previous generations of stars. And that's all. Thank you.
Hello. Hello. No. Yeah. Okay. Hello. I'm Mikel Millán Irigoyen, a postdoctoral fellow at MPA, and I'm here to present the second release of HRB Bob-Star models. HRB Bob-Star, it's a spectral synthesis code made especially devoted to make high-resolution spectra and to take any kind of combination of stellar evolutionary tracks and atmosphere models. In this case, we use the evolutionary tracks from the Padua group and a variety of atmosphere models. I don't have time to get into details, but adding all that up, I've made the models that have like 106 models from 0.1 mega year until very old populations, and this with metallicities ranging from 1% solar to 2.5 times solar, with a highest spectral resolution of any other models available yet, ranging from near UV to near infrared. They have been tested, the HRB Bob-Star models, in several full spectral fitting and steady fitting codes, such as FADO, Starlight, JWST. You can download in this QR code or in hrbobstar.com. And then using these models, what I made first is to make against different comparisons. We compared with different empirical models, and we found an agreement between all the models in the optical, but they disagree in the near infrared that will affect the result that we obtain in the ages and metallicities, but especially in the ages. And then finally, we analyzed 33 high quality spectra of dwarf galaxies of Manga Galaxy survey using FADO to obtain the mass metallicity relation. We obtain a high dispersion in the metallicity for the mass range that we have, but as the majority of them were like star forming, we are having higher metallicities than the average of the dwarf galaxies, in agreement with other studies that have been studying dwarf galaxies with star forming galaxies. Thank you.
Hello, my name is Sarah Down. I'm a graduate student at GMU, and I want to present a couple of our targets from our JWST Cycle 1 program. The program was originally designed to look at local analogs of possible early type galaxies, and given the low masses of our galaxies, possibly maybe find a IMBH, because that would be cool. Unfortunately, looking at the near-spec data, I should point out these targets were selected because of their extremely red WISE colors, which we typically see as indicative of AGN. However, looking at the near-spec data, we don't really see any definitive signs of an AGN. There are no coronal lines, there are no broad lines. However, there are still super interesting targets, given that the WISE sources are unresolved in the JWST data. Therefore, they're very, very compact, and so all of this WISE color is coming from areas of either parsec or tens of parsec scales. And then also, as you can see in the spectral plot over here, the nuclear region is the only one with this very steep continuum slope. Everything outside the nucleus is fairly flat. And so given the non-definitive AGN status, we are thinking that these are early starburst galaxies. The J1201 does not have any PAH or CO absorption features, so we think it's a little bit earlier than J1601, which does, as well as some Wolf-Rayet features. And so if you are interested in these targets, I suggest checking out our papers. We have the J1201 is already published, and the J1601 is currently in prep and will be out soon. Thank you.
Hi everyone, my name is Sophia and I'm a second year graduate student at the CFA. Thank you very much to the organizers for the opportunity to speak. Today I wanted to talk about some ongoing work with the Typhoon survey. So here I'm showing a H-alpha map of the nearby local irregular dwarf galaxy NGC 3109. The white contours are H2 regions selected based on the H-alpha surface brightness, and blue dots are OB stars that are spectroscopically classified in a paper led by Abby Mintz and was also introduced by Christy Ober earlier from the Tempos survey. And so with this, we're trying to basically characterize the H2 regions and the ISM properties in the galaxy and link it to the properties of these massive stars and try and understand that. So we have other data as well as part of the Typhoon survey. So this uses a long slit that's been stepped across the field of the galaxy to build up the full field of view. And we have other dwarfs as well if you're interested. We have sextans A, WLM, IC 5152, and several others as well. So if you're interested, feel free to come talk to me, or you can visit the website. Thank you.
All right, one last round of applause for all of our speakers for this. And before we break, we just want to have thank Brittany for doing everything for the baseball game. Brittany's going to give some updates for you.
Just two quick ones. I know you guys probably want to get out of here. Number one, if you are in section 316, row 2, I'm going to ask you all to just add 1 to your seat. We just want everyone to shift down 1. I made a little mess up, and it's easier than having you all send me your tickets back and resend them out. So just shift down 1. If you're in 17, sit in 18. If you're in 18, sit in 19. Very simple. Number 2, I do have tickets left if anyone's interested in still going. So come find me. I'll stick around for a couple minutes during the break. I think I have 4. And they're just $33 each. There's a bunch of us going. It's going to be fun. And weather looks like it's going to be great. Last year we got rained out and had to refund everyone. So it looks like we're going to do great. I have no allegiance. Ignore my t-shirt. But the Yankees did beat the O's last night. So.
What was the section you wanted to read?
Section 316, if you're in row 2, everyone shift down 1, just so I can accommodate a little mix-up that I did. And that's all. Thanks for coming.
All right, thanks, Brittany. We do have posters at the break, so please, by all means, go check out the posters during the break, and then we will see you again at 3:30.
What do I need to know? I'm chairing the next session.
So